I'm Dave Landsman. I work I manage the industry standards group at Western Digital. I'm actually, a little bit to my surprise, kind of a veteran of NVMe. I've been involved in NVMe since 2011 and on the board since 2012. So I've been around for a while and watched it grow, and it was good to see Peter's overview of how we've progressed. So what I wanted to talk about here was there's been, before I get into zone namespaces proper, there's been kind of a debate over the last couple of years about, and it's manifested itself in, the sexy sound bites are open channel versus traditional NVMe SSD. But what it's really been about is the emergence of a couple of new major use cases that have been coming out of the cloud vendors, primarily. And it's really about new use cases. And NVMe has stood back and looked at this and said, well, how do we react to these use cases? How do we integrate them into NVMe? So the first major new use case category, I'll call I/O isolation. So Nick talked about that in the last talk a little bit, but the focus here is on controlling latency and controlling QoS. And the approach, the technical approach, has been about getting full host control over the SSD physical topology and really managing one SSD as multiple SSDs. So this is kind of the open channel model, right? And the other use case, which wasn't as apparent initially, at least, was what I'll call right amp reduction. So there was a segment of people that were focusing on capacity and cost, using QLC NAND, getting the highest possible capacity and lowest cost. And what they were trying to do is enable a collaboration between the host and the SSD on garbage collection and wear leveling, kind of more at a logical level than actually managing the detailed physical properties of the devices. So, and there was a lot of, so in this whole open channel debate, there's been a lot of percolation in the environment. Various vendors have their own stacks, and so NVMe stood back in this and started looking how should we address these new needs that are evolving. So on the I/O isolation front, we added I/O determinism to 1.4, and so that we defined sets and endurance groups as a way to bracket the topology. So sets and endurance groups are a way to, draw lines around physical resources in the drive, and so that you segment one drive into many. And then predictable latency mode and some other protocol enhancements that were put in allow the drive and the host to talk together about how they control the drive being in a deterministic or a non-deterministic latency mode. So we talked about that already. I won't belabor it. Whoops. Wrong button. Okay, so we're now, to take this a little further, we're going to add endurance group management, and this is what Mark and Paul are going to talk about later. So that's about getting more granular with how we segment these things. You'll notice in the previous slide I kind of had these as rectangular, and it's kind of simpler, but if you take this to its logical conclusion, some people want to dynamically allocate resources within the drive, configure it, and be able to, optimize along channels and physical resources. So the next talk will address this and how we're trying to bring that into NVMe. As far as the right amp reduction use case, we've added what we call zone namespaces to NVMe. So we're working on this spec in the committee now. And the basic idea here is that we divide the logical address space into fixed size ranges, and we enforce sequential write rules. So you have to write these. So the namespace is divided into zones, and each zone must be written sequentially. And the drive manages a write pointer, and if you violate the sequential rules, you get an error. So we enforce some behavior, and what this allows us to do is kind of match the workload characteristics to the natural patterns within the flash in terms of erase blocks. So I'll talk about that a little further. One thing to note is that zone block storage that I've just described at a high level is already in hard drives. It's kind of ironic in some ways. A few years ago, when SMR, or shingled magnetic recording drives, were introduced, people wanted to take advantage of the capacity in these drives, and so the way SMR works is, the conventional HDD laid out its tracks in discrete bands like this, and with SMR you actually overlap the tracks, and you can do this because when you read the data, you can read it in a more narrow physical range. The read head is narrower than the write head, so you can lay down the tracks more efficiently, get more areal density, and then you can read it back. The problem with SMR is that when you write stuff, you are actually affecting adjacent tracks. So the solution was to break the drive into fixed size zones and format it for fixed regions, and then allow a zone block protocol so that you can mitigate the effects of this read, modify, write cycle. And it's kind of ironic because when SMR came online, it brought some of the same problems we've always had in SSDs to the hard drives. But anyway, so this model has existed. Now, why do we want a zoned model for SSDs? Well, kind of the same reason. It's to take advantage of higher capacity. So in particular with quad level cell flash, as we increase the bit density in flash, we're managing more narrow voltage levels, and the errors get more prominent, and write performance gets lower. And so you buy capacity, but you get lower endurance, lower performance, and also you get more DRAM in the SSD because as the capacity explodes, the logical to physical mapping tables just get bigger. So when you're talking about multi-terabyte drives, the DRAM component in an SSD gets big. So what we wanted to do is introduce this zone block model for SSDs, and it's a very natural model for SSDs because SSDs are already, flash is already kind of a zone technology. You have erase blocks that you need to write, and you want to fill them up entirely before you erase them. Otherwise, you're going to waste space, and you're going to do a lot of extra garbage collection and data movement around in the device. So making the zone extension on the right side to an SSD was very natural. We divide the LBA space into zones, and the host and SSD cooperate. They kind of distribute the FTL. So whereas the entire, on the left side here in a conventional SSD, the drive was doing everything. We were reading and writing LBAs, 512 bytes or some small amount, and the drive was doing all of the management. And in Zoned Namespaces, in the zone block model, we cooperate between the host and the device. And we don't have to worry about topology provisioning. This is all about logical address space. So we're not dealing with sets and endurance groups, things like that. But you do get, so what you do is you reduce the write amplification and you reduce internal data movement, and that in turn mitigates the problems that we see with higher capacity flash. So we reduce wear, we improve latency because we're writing sequentially, and we're not doing as much garbage collection, so that the drive is more consistent in its response. And we reduce DRAM because now the buckets that we're managing are not LBAs and individual LBAs, but bigger zones, which are often, we try and match to erase blocks and things in the drive. The other thing is that I got lazy and didn't put it on the slide, but a conventional SSD is going to have some more capacity down here somewhere for over provisioning, right? So we have some extra spares to move things around in just so we can efficiently drive, so we can efficiently garbage collect. In a zone model, because we have less garbage collection and less data movement, we can reduce the amount of over-provisioning that we have and give more of that capacity to the customers who, that makes them very happy because they're looking for the most bang for their dollar in terms of the bits of flash. So the other big reason why we wanted to bring zone block storage to the SSD ecosystem is because we have already started building a software infrastructure in the hard drive SMR system to address zone storage. So we've begun since SMR, the advent of SMR, we've begun optimizing various levels in the stack. So we started obviously by building the zone block device model for SCSI and ATA. And we've a lot of hours and a lot of committees, as my friend David was mentioning before the talk. We've a lot of blood, sweat, and tears went into this. And what we've been able to do, so after establishing the zone block device model, we then started looking at different optimization paths within the stack. So the first and easiest level of optimization was just to modify the block device interface so that we have a mapping, a device mapper to the zone block device. So that it doesn't really buy you too much performance or any, but we just had to literally, if you wanted to start with a legacy app and go down this path on the left, you needed to map, you needed to connect the stack to the block layer. You can further optimize things by, say, adding a modified a file system that's modified that understands zone block devices, because the file system now knows what LBAs it's got in the file, and it can then talk directly to the zone block layer, and we get better optimization. And then you can also go the next step, which is it's the hardest, and it takes some more time, and people always hate to do this, but this allows you, if you go right to the app and you ignore the file system entirely, you can get even more optimization. For example, a database may use a zone as a container for an object. So, and then now that since we put all this infrastructure in place, now we're in the process in the Linux ecosystem of adding hooks and things for ZNS, so that we can bring NVMe zone drives into this milieu. And then in other spaces, Microsoft has talked about using zone storage, and they're adapting their stack, and so we're going to see zone storage proliferate. We're quite sure in the next year or so. So as far as the technical proposal, actually, I don't know, well, some people were here last session or not, but so the zone commands, it's basically the NVMe command set plus a couple of things. There's a Zone Append command, and there's some zone management commands too, which I'll talk about in a minute. And as far as the zone types, those of you familiar with the ZAC CBC model, there's a number of different zone types. For ZNS, we picked just sequential write required. So basically, a zone, you have to write it sequential, and you have to obey the write pointer rules, or else the drive will start rejecting IOs. We are looking to this point, excuse me, we are looking at some potential add-ons to this. For example, there are some use cases where a host might want to write in this region here, either right before the write pointer, I guess. I won't bother with you, but do a little bit of random writing, and until the data settles down. So do that in a buffer somewhere, and then commit that to the zone sequentially. So there's this kind of hierarchy. So we may end up defining a new zone type or a modification of the zone model, like a modification to a zone state. But for now, in the initial spec, we'll just have sequential write required and try and keep it pretty simple. Now, there are a couple things where we're enhancing the zone model for SSDs, and that's in the area of zone capacity and this thing called Zone Append, which I'll talk about. So before I talk about zone capacity, just here's the, hopefully you can see it, not too bad. This is the zone, the ZNS state machine, and it uses the same basic states that ZAC and ZBC use. So we have empty, full, implicit open, explicit open. So implicit open is if you do a write to a zone, it just opens. And explicit open, as you might imagine, is when a command opens the zone. So we have a number of states, and state changes can be caused by either write commands, zone management commands, or device resets. Now the size versus capacity is something that's actually already part of NVMe. NVMe namespaces have a size attribute, which is their physical size, and they have a capacity, which is the highest LBA that can be written in that namespace. And we're adding the similar capability to zones. And the reason is, there's a couple of reasons. The main one is that hosts like to think about things in powers of 2, and Flash isn't always in powers of 2. So we want the zone size to be fixed, the power of 2, to make it easy for hosts to deal with this, the address space. But the actual capacity of the zone may be less. And in some cases, the capacity of the zone may be variable, either due to defects or other, the drive taking a zone offline, things like that. So this whole notion of a variable capacity zone is being built into the spec. It's pretty subtle and a lot of stuff to work through there, but it's being requested by customers. Zone Append is a new way it's a way to get around a problem that exists in ZAC and CBC. So in the hard drive case, we require strict write ordering, and this kind of limits performance. And so we can try and mitigate the performance by adding multiple writers to a zone. So the chart right now is showing, so the red bars are showing performance on this benchmark, and as let's see, so we're talking about one zone in each of these bars, and as you go across the horizontal axis, we're adding number of writers. And as you can see, when we add multiple writers, we go from one writer to 2 writers, we actually drop performance and it stays down because we're seeing contention. So you don't scale well in an SSD ZNS drive when you just add multiple writers. Now we can improve this somewhat by writing to multiple zones. So the purple arrows are they showing purple? Yeah. We're now writing 4 zones, so we're distributing, and we get better performance. With Zone Append, and I have one more slide that talks about kind of how Zone Append works schematically. We see scaling performance. So, and Zone Append is where you append data to a zone with an implicit write pointer, and the drive actually returns the LBA to the host and says, here's where I put the block in the zone. So it returns an offset. So a quick look at how Zone Append works. So this is on the left side. You see the zone write, where traditionally you do 3 writes, and the host orders them, and the write pointer moves, and so the host is serializing the I/O and is forced to kind of stay at low queue depth. With HDDs, the lock contention is not a problem, like I said, because the performance is not so high. But with SSDs, as we saw, we get lock contention, and it's problematic. With Zone Append, you just issue 3 writes. You don't worry about their ordering, right? So the host doesn't have to serialize and can potentially get to higher queue depth. And this method can scale for both HDDs and SSDs, although right now it's probably going to get adopted for the NVMe version alone. So in summary, Zoned Namespaces standardizes an interface for an important evolving use case in the cloud particularly in the cloud, and also in the storage array environment where we need streaming and sequential workloads that are well tuned. And in this mode, the host and the SSD can cooperate together and kind of impedance match between the I/O pattern and the natural structures of the flash to create get lower write amplification and thus reduce wear and reduce the DRAM in the SSD and reduce over provisioning. And the other good thing about Zoned Namespaces is that it then puts SSDs in the same, or it allows us to manage SSDs in a similar software model that we're managing SMR HDDs. So we can get synergy for customers who want to use both solutions. And the specification is it's essentially feature complete in the committee. It's not done. There's still a few things we're arguing about, but we'll probably publish it, in a couple of months, is my guess. So it's getting very close. So that's the end.